Okay, so we're going to look at a couple of friction problems. I'm just going to work through them with you so we can get some practice working on net force equations and drawing free body diagrams. So for this first scenario, there's a book that we're pushing against the wall to hold in place. And so the question here, so if there's a coefficient of friction of 0.7, it's kind of high. Let's say the coefficient of friction is 0.2 between the book and the wall. And so the question is, well, with how much force do we have to push, okay, to keep it in place? Alright, so to start here, I'm going to draw a net force equation. So we have downward weight of the, a free body diagram. We have the downward weight of the book. It's actually being held in place by static friction, okay, and we'll say that this would be the maximum static friction, okay, it would be 0.2. And then we're pushing into the wall with this force F, and then it's being balanced by the normal force coming back out of the wall, okay? And we want to solve for this, okay? So we can do this by writing net force equations. We'll start by writing one for up and down, okay? In both cases, these are balanced, all right? So that means the sum of the forces should be equal to 0. Let's start with the y direction. So going up, we'll say that up is positive, okay? And so a reminder, a net force equation is just an equation where you add all the forces acting in that direction. So we have two forces acting in that direction. And we can add them in either order. Let's start with weight, okay? So we have weight and static friction. Now because weight is acting downward, we're going to say, okay, since up is positive and weight is downward, we're going to say this is negative. Alright? So we can now say, well, weight is equal to mg. Static friction is equal to mu times the normal force. Okay? And so we say, okay, mg equal to mu, since that's 0, times the normal force. And we're kind of stuck here. There's not much more we can do. We're going to need to write another equation for the net force in the x direction. So when we write the net force equation for x, again it's balanced, so this will be equal to 0. And we can say, okay, we have these two forces acting. We'll say that this way is positive. So we have Fn, normal force, and this applied force. Okay? And we know that since this is acting in this negative direction, we'll say that that's a negative force. Since that's acting in the positive direction, we'll say that's a positive force. Then we say, okay, we can solve this and say that the force applied is equal to the normal force. So we can then say, alright, applied force in here for normal force. And so mg equals mu times the applied force. And so the applied force would be equal to mg over mu. So that would be 10. We'll say that g is 10 for this one, divided by 0.2. So that's 100 divided by 0.2, which is, I think, 500 newtons probably. Okay, so we require 500 newtons of force in order to hold this book in place, given the slipperiness of this surface. And you can see that as mu gets bigger, then we require less force to hold it in place, because there's a stronger frictional force between the two surfaces. Okay, this next one is similar to one you worked on before, and so I'm going to do this one too. Again, we'll start with the free body diagram. So we have this block that we're pulling at an angle with some force T, tension, and we're pulling it at a constant speed, so acceleration is 0. So we can say, okay, the sum of the forces acting here, well, let's start with the free body diagram. So we have tension up here at an angle, 20 degrees. We have a normal force. We have friction, would be kinetic friction in this case, and then we have the weight. Okay, and so let's start with the net force equation for the y direction. Alright, so we have 1, 2, 3 forces acting in the y direction. So the sum of the forces for y, it's balanced this way, so it's going to be equal to 0. And we can say, okay, let's say up is positive. So we add all the forces together. We have normal force and tension and weight. Now, normal force and tension are positive because they're up. Weight is going to be negative because it's down. So this is minus weight. And at this point, we could say, okay, we can maybe solve this for tension. We could solve this for normal force. Let's solve it for normal force. So we could say the normal force is equal to, we add this over and subtract that over, so W minus, and this would be Ty, so T sine of 20, the part of T that's acting in the y direction. So minus T sine of 20. Okay, now let's do a net force equation for X. Okay, so we have two forces acting horizontally, so they add to be 0. We have T cosine of 20, and kinetic friction, we'll say that this way is positive, which means that kinetic friction would be negative, so we'll make this a minus. And we know that kinetic friction is equal to mu, coefficient of friction, times the normal force. So we can say, okay, 0 equals T times cosine of 20 minus mu times the normal force. And we know that this is equal to the normal force. So we can say, okay, 0 equals T cosine of 20 minus parentheses, or mu, parentheses, W minus T sine 20. Okay? At this point, it becomes a bunch of algebra. Okay, we know that mu is equal to 0.3. We know that W is equal to mg, 10 kilograms, so we'll say that W is 100 newtons. And then we can solve it from there. Okay? We can also say that T cos of 20 has to be equal to negative mu times 100 minus T sine of 20. And then from here, it's just working it out. Okay? I can put the answer up, but I'm not going to take the time to show this to you. I just don't, I mean, if you want to work on this in class, we can, but I don't want to force you to sit through me spending 5 minutes of doing algebra. Okay, so I worked it out, and I got that T was 120 newtons. Okay, and so success here is going to come down to drawing a free body diagram and setting up these net force equations. The algebra here at the end is even secondary to being able to set up these equations. I don't care that you can solve this, like solve them, like more important is being able to set them up and understand how they fit together. Okay, we're going to do one more in this video where there's acceleration, okay, and that will wrap up this video. So last one here, we have acceleration. This object is being pulled upward at this angle, and this time instead of moving at a constant speed sliding along, we're actually causing it to accelerate. And so the question here is, what is the coefficient of friction between these surfaces? Okay, so we have tension up here at 150 newtons at an angle of 30 degrees. We have an upward normal force. We have the downward weight. And then we have kinetic friction. Okay, so to get started, let's do a net force equation for y. We can say 0 equals, acting upward, we have normal force plus the y component of this 150 Newton force minus the total weight. And so the normal force is going to be equal to the weight minus 150 times sine of 30. So this would be, let's change the mass. We're going to say the mass then is 15 kilograms. I'm making a mess of this problem. Let's say it is 8 kilograms. Alright. Which means that the normal force would be, let's see, 8 times 10 would be 80 newtons. This would be sine of 30 is 1/2. 1/2 times 150, 75 newtons. That means we have a normal force of 5 newtons. As I said, making a mess of this problem already. Okay, so now we can do net force equation for x. in the x direction, we're having acceleration, so we're going to say m times a equals, so we use ma here instead of 0 because it's accelerating. Now we're going to add those x forces. So we have kinetic friction and the x component of this pull here, so 150 cos 30. Now this is negative because it's pulling backwards, going the opposite way. And then A we said was 1 meter per second squared. Okay? And then mass 8 kilograms. So we plug these in, we say, okay, 8 kilograms times 1 meter per second squared gives us 8 newtons. This is negative F of K. And then 150 times cosine of 30 is going to be about 150 newtons. So we get that F of K equal to 142 newtons. Okay, and so now if we want to solve for the coefficient of friction, we say, okay, friction is equal to mu times the normal force. So 142 newtons equal to mu, which we're solving for, times our normal force of 5 newtons. And this is going to be a coefficient of friction of something astronomical. This is the stickiest substance ever known to man. So 28.4. So essentially, what this is saying is, if you have an object sitting on a surface, this particular object sitting on this particular surface, it would take 28 times as much force to push it horizontally than to just lift it up. So I guess that could happen, like maybe if you're dragging something through the mud, potentially. But you can see why I was starting to realize at the beginning when I got a really weird value for normal force that this is a bad question, because generally coefficient of friction will be less than 1. Or there's some having trouble speaking. There are some circumstances where this will be close to 1 and potentially even greater than 1, but those are pretty rare. Generally, there's not surfaces where it's harder to push than it is to lift something up. And there will be some surfaces where it's really small, like 0.01 or like 0.005. Okay? Anyway, I hope this video is helpful and you're starting to get the hang of these net force equations and free body diagrams a little bit.